All right, good morning. Let's get started. If you're online, remember to turn on your cameras. So today we are going to continue our management zone exercise. This is how it looks like on my side. So please go ahead and launch that RStudio project. So last time we stopped at the smoothing zones, or we were about to do that part of it. If, like myself, you don't have, your environment is empty, so your variables are not there, we're gonna have to run some chunks. Do not hit the run all above button, because as you recall, that includes that the chunk that we run a lot of indices to decide the number of zones, and that may take a while. So if you run all above, that's gonna get you stuck there for a little bit. So instead of running all above, let's just go and run the chunks that we need to get to that point if you don't have your objects yet. So running the setup, as you remember, we always need to load the packages when we're opening a new R session, importing the OLV dataset, importing the boundary. We can skip the EDA. We can skip the k-means explanation. Next thing that we come to is the chunk called all-vn. So we need to run that chunk. We don't need to run this first k-means here. That was just us exploring. We do not need to run any of the chunks that help us to decide the number of k. We have to run the mod km2 chunk, as that was our final decision on the number of k's. Let's see, I don't remember. I think we have to run the zone df, so let's just go ahead and do that. Create zone df. We don't have to rerun this cluster map because that's already done. And then we end up here. Okay, so this is basically where we stopped. Let's just talk about it. So the last thing that we mentioned last class was looking at the way that the cluster looks like right now. It has some like intruders, I guess, of very small areas of one zone inside of the other, right? So we see a whole bunch of black dots or black pixels inside of the orange cluster, and then we also see the opposite, especially on this top area here on the cluster. On the black cluster, we see a lot of orange points that are kind of like, maybe, we have to define how we manage that, or what we do with them, because, again, this may be such a small area that is not worth it for a variable rate equipment to be really trying to change rate for such a small area and then change back again. So these are things that we normally want to remove them before actually using this map for variable rate of any sort. Okay, so one way of course, like, you could come here and manually just change them. I guess in R, the way to do that is not as, there's not a good way of like pointing, clicking, and just changing that. There are other ways we could change this, but I'm not gonna be showing you those. Instead, we want to use a smoothing filter. So what is a smoothing filter? I'm going to run this chunk here. If you were having issues with the nadar package before, don't worry, you can always access this website and you can see that figure there. But I want to have that here in the script. So just so we understand what is a smoothing filter or a focal filter, and how can we use that for our advantage. So smoothing filters are used a lot, especially with raster files. Of course, we don't have a raster, but it's still the same concept. But what happens is they're called smoothing filters because normally what they're doing is using like a mean or average function, and they call a window because they take into account a certain number of neighboring pixels to do that averaging function, for example. So in this example here, what we're seeing is we have this black outline is the window. So it would be a 3x3 matrix that's been used as a window. And then it goes on that pixel in the middle, which in this case has a value of 8, and then looks at all of its neighbors within the focal window and takes the average of all of them and assigns that average value to that middle pixel. In this case here, I think it's actually, the function that's using is not average, I think is the minimum. So what happens is within this window, for that center pixel, it looks at all of the neighbors and extracts the one with the minimal value and assigns that value to that center pixel. So in this case, this 8 becomes 0 because 0 was the minimum value within this window. And then the window just moves one column to the right and does the same thing continuously, and then starts moving below after that. So it's a moving window that for each time it moves, the center pixel changes and the neighboring pixels also change. And it is extracting some type of information and is transposing that information to a new object where it has that summarized information by the size of the window that you create. So this is a smoothing window or a kernel. Those are some of the names that they're referred to, and they're really useful, especially in this case here, because if you think of it, if we create a window of a given size and we say, give me the average or give me the minimum or maximum, it will potentially remove these like loners that we see here on both of the clusters. But that's kind of what we're going to do next. To do that, we have to have a grid, right? So I left you the code here because we already did this a lot. If you recall, one of the first chunks on this exercise was to bring in the boundary. So we're going to use that boundary again and create a grid that is again 10 by 10, just like we've been using before. So we can just go ahead and run that chunk. And I do have a couple of packages here that we're going to be needing to develop the following chunk. I do not remember if I asked you already to install the stars extra. So if you have a cursor in there, just run that line of code. If it gives you an error saying stars extra package does not exist, you know how to fix that. Just go ahead and install stars extra package. And gstat you already have because that's the one that we do the interpolation. Okay, so again, just refreshing your head before we start working here. Our goal is to develop this, to apply a smoothing window to our original unsmoothed zone assignment. So we clear out some of these intrusions, I guess, that we have of one cluster inside of the other, especially when they're like too small, right? So especially these like one cell intrusions that are really not useful to have in there. Okay, so we are going to save this result to an object called zone_s for smooth. We're starting with zone df, and I left you already. I'm selecting cluster. So if I just add a comment there just to cancel the flow and run it just through here and print zone s. Zone s at this point still has a 3,695 rows, and now just has the cluster column and the geometry column. And the cluster column is either 1 or 2, right? It's just our cluster ID coming from the k-means result. Okay, so if you want to go ahead, so this, we're going to be developing this code here together. It's going to be a good amount of coding. So please follow along with me so you don't get lost. Okay, so the first thing that I want to do here is if we just print zone s as is now, as I just like stop flow there and printed it, this is a polygon type of vector object. For the window, yes.
I went to install the stars extra, and then it said it ran, and then I went to go run the library stars extra, and it still said there's no package called stars extra, even though right before it I have install.packages parentheses stars extra.
Huh. Okay, that is kind of weird. I'm not sure why that would be. Let me try installing on my side and see if Install packages, stars extra, I run that. I want
Oh,
to,
I didn't put it in quotations. Let me take that back. Let me try this again.
yeah, maybe that's what's causing it.
Yeah, that makes more sense. 1 second.
Yeah.
All right, it's downloading. It looks like it's downloading for real this time. All right, if it messes up, I'll holler at you.
Yeah, it's kind of you know, a difference, I guess, that install packages always requires the quotation marks, and the library pack or library function, you can choose like to have it or not have it, and it doesn't make a difference. But on the install packages, we always need to have the quotation marks there. All right, so the first thing that we want to do here is go from polygon to a point type of vector file. There may be a couple ways of doing that, but the one I want to show you here is a function called st_cast. And then you open and close quotation marks and you type point. I believe point has to be all uppercase. I guess I never tried to do differently, but this is how the documentation specifies. So I encourage you to do that as well. If we run that, and now I just want to print it below so we see the outcome of it. It's still well, actually now we have a lot more data rows for some reason. But it is of type point, which is what I wanted to do at this stage here. Now, so to do this type of operations, we're going to use some functions that require to transform this from geometry to XY. And really everything I'm telling you here, I'm kind of narrating the steps, but you don't really have to worry too much about them because it's very specific. So you don't have to remember everything we're doing step by step, but I still nonetheless tell you what we're doing step by step. So just add a pipe there. If you go below the next comment there, to transform this from geometry to XY, which is what we need to run the focal function, we use a function called st_sfc to XY. So I guess the name is just implying that we're going from SFC to XY format. If you run it at this point and you print zone S, it's basically more on a stars type of object now, and we went from having a geometry to have XY type of coordinates, which again, don't need to worry too much about it. It's just the steps needed to accomplish what we want, which is to run the focal window. So add a pipe there, go below the next comment. The next step here is I just want to, it seems like it's already as a stars object, but for some reason in my code, I have it transforming to raster again. So maybe let's just go ahead and do it in case, when I developed this, that was necessary. So the function that we're going to use is st_s_stars to force this to become a stars object. And then now being in a raster format is where we're really going to apply that focal filter function. So add a pipe. After that, come below the next comment. The function here, the function name is called focal2, coming from that stars extra package that we just installed. And it has a few arguments that we're going to change here. So the first one is W. So W is where we specify the matrix that we want to have. So when I showed you this example here, this is a 3x3 matrix, right? So we just need to specify what size matrix we're using. So to do that, to specify, we're actually going to give it the matrix already. To do that, to create a matrix in R, we use a function called matrix. And we're going to say here, let's see, I have the arguments 1.5 or (5,5). If I just run this below, so just the matrix part, so you see what that does. If I run it, this is what I get as an output. So it's basically creating a matrix, so not a data frame. If you recall, a matrix has columns and rows, and they're never named, right? They're just, this is just the way that the brackets here is just a notation specifying column position and row position, but this is just a matrix, right? And it's just filling that matrix with values of 1, and it is of size 5 by 5 because it has 5 columns and 5 rows. So we're given this matrix as that argument for the focal window. The next thing that we're going to do is, so after you close that matrix parentheses, but still within focal to function, add a comma. I want to break code just to make it easier to see. It has an argument called fun for function. Let's use the function mean in this case. And then lastly, I just want to add a comma and add a last argument here. That's the na.rm equals true. So that removes any NA values and still does the computation of mean for us. Okay, so I just want to stop for a moment here and relate what we just did on this function back to what we saw on the figure of the focal window above. So here we're given it a matrix that is 5 by 5, so 5 rows by 5 columns, and we're asking it to use a function of mean. So if we were to come back to this example, this is a 3 by 3, right? So 3 columns, 3 rows, 3 by 3 matrix. And here is using a function of minimum, I believe, because if this cell that originally was 8 returned to 0, it cannot be the mean of these values. The mean of these values would be greater than 0, right? So my guess is that in this example here is probably using the minimum function as the function of this window and just returning back to that center cell, the minimum value that's found within that neighborhood within the focal window. So we're asking for a larger size matrix and also different function. We're asking for the mean. Okay, so I mean, we could run it until here and just inspect to see what zone S looks like at this stage. It's still a stars object. You know, we see that it has so because we only have 2 classes in our clusters, either 1 or 2, we see that now it has a mean, actual mean value, because now if we were to print those values, they would be, most likely they would not be 1 or 2s anymore. They're going to be a mix. Well, I guess we would still have 1s and 2s. So if you think of it, if a window is right here and it's taking the average of, and all pixels around the middle pixel are the same number, and it's still going to return that same number. However, if you imagine that on that black pixel that I'm just circling right now, when that is the middle pixel and it's taking the average of all the points around it, that average is going to be 2. So it's going to assign that black to 2. So going from 1 to 2. That's basically what it has done already. We just have not plotted it. So we're not seeing that yet, but that's what it has. It just.
Dr. Masters.
Yes.
So what is the criteria behind setting up the matrix as 5 by 5? I mean, can we do 6 by 6 or 7 by 7 like that? I mean, why did we specifically do 5 by 5?
That's a great question, Anis. Thank you. So this is what I'm proposing as our initial attempt. You will actually have you all will actually have a chance to play around with that during the assignment. So we're going to use a different different matrix size and also a different summarizing function. So, but that's a great, for right now, that's arbitrary. It's really just my initial suggestion. Yeah, but that's a great question. Yeah, if you're doing this in your applications, you should probably test a few different sizes, maybe some different functions as well, and decide which one makes the most sense when you plot the results, right? That's we only know what's happened when we plot the results and make maps. And so that's what we're going to be doing at some point today as well. And also something to point out, okay? Really, really important for our understanding here. So if we have a 3 by 3, matrix on the window here, it will end up that we have a center cell, right? So this is the center cell that the window can change considering the neighbors. If we do 5 by 5, let me also print that here below so you can see what I'm trying to say. A 5 by 5 also has a center cell, right? So this number one here is the center cell of that 5x5, and it has all the neighborings around it. However, look what happens if we do with an even number. So let's do a 2x2 matrix instead. There's no center cell, right? What about a 4x4? There's no center cell again, right? So if we do a matrix with an even number, it's not going to work because it needs to have a center cell that it can change based on its neighboring cells. And if you do a matrix with an even number, that you don't have a center cell. So I guess the only restriction perhaps is that you need to use a odd numbered matrix size for this to work. All right, so now we've been even though we have used raster objects, right now it is a raster, and we've used in the past as well. I do want to bring that back to vector just so it's easier for us to look at the data and to have the columns that match with other data layers as well. So let's just bring this back from raster to vector. And this is really interesting. So, this function here we have used already a lot. You've been asked about this function a lot, but maybe we haven't used as much in this context. So if I want to bring something from whatever format it is, whatever class it is, and transform that to vector, we use st_s_sf. Even though in the past we've used this a lot when we were bringing CSV files and we had X and Y columns, in which case we do have to specify chords equals to the name of the column that have the coordinates. In this case, we don't have to specify that because that information is already part of the raster object that's coming until this point. Okay, so let me run this, and I just wanna let me see if I can. I don't think I can plot this as, so you don't have to do the change I'm doing here, but I just want to see if I can show you easily what this is right now. Okay, let me change something I'm just doing some changes on the fly here because I want to show you what the result looks like right now and why we're continuing to change it. Okay, that didn't work. Yeah, so never mind. I just wanted to show you that. So perhaps I can show you up here. We don't have, so when we do the window, we're still missing some data points along the edge so that, it doesn't extend all the way to the boundary. And I do want it to extend to the boundary because, if this is a producer that we're giving this layer to, they still need to apply something near the boundary. So I just want to give or create those values that right now are missing around the boundary. I want to give here a pipe, and what, if I'm telling you that I want to fill in some gaps, I hope that your mind went already to interpolation. So that's what we're going to do here. It's really, and I want you to pay attention here because, we have done interpolation a handful of times before, but they were always like, we had different chunks, one for the gstat function, one for the predict function. They all were separated. Right now, we're basically just embedding that into this workflow and not even like giving that much attention, but I just wanted to see that. So, all right, so let's interpolate here. I want to interpolate that cluster all the way to the boundary. Now that it has already been smoothed out, what is the function that we need? I mean, we need two functions, right, to interpolate. What is the first one?
gstat.
Yes, gstat is the first one, right? Was that Sekar or Anish?
Yes, Sekar.
Thanks, Sekar. Yes, so gstat is the first one, right? So let's just go ahead and write that down. If you recall, it has this argument called formula, where we're gonna say here cluster till day one, because we want to interpolate cluster. We add a comma here, and if you recall, this also has a data argument. Now, the thing is, the data that we're gonna give it is basically the data that's coming through that pipe flow up until here. And the way that we specify that is just with a dot. We just give it a dot and it knows that the data that it should place right here is whatever is coming from above. So if you recall, the gstat just sets the formula, but now we have to actually do the interpolation. Let me ask someone else, what is the next function that we need to do here to actually interpolate this? Guys, both? Yes, thanks, both. Predicts, right? So predict is the function that we give here, and this is really where we give the grid that we created above. So this is where we created the grid to do the interpolation. We're just gonna give that object right here. If you recall, when we were doing this in different steps and different chunks, the predict function also, we needed to give the data as the first argument and then the grid. But because the data is already coming through the pipe flow, we just give it the grid and it knows how to handle it. Oh, and I got an error. Let's see what's going on. Oh, I didn't load. Yeah, so I got an error here, and it was saying that could not find function gstat. So this function here that I asked to use, it's probably because I forgot to run the library gstat package, or to load the gstat package using the library function. So when you do that and you run it, it should run all right. All right, so now we went through. So if you recall, gstat and predict returns you a raster, a stars object. We do want to bring that back to SF again. So let's use a pipe. Again, we're going to use st_s_sf to do that. And here's, I want to show you, now I want to print zone S, because now we have the column called cluster, and I want to show you just a little bit of what that is now. So if you recall, the interpolation returns us the var1 pred column, that at least that's on my side is returning that column. And then we have these values here that are not ones or twos anymore, they're fractions, right? So I just want to ask for a summary to see. So var1 pred is going from 1.038 to 1.947. Okay, so this creates some issues, right? Because now our cells are not ones or twos anymore. They're actually a continuum between 1 and 2. And that is not very helpful, right? Because we do need them to be either 1 or 2 after going through the focal window that we applied. So at least when you have only 2 classes, one trick that you can do is basically just round them, right? So if I just come here and I round these values and I ask that I want to round them without any decimal points, it will round round either to 1 or 2, right? And that's one quick way to force that continuous variable to become either 1 or 2 again. So if you come here at a pipe, before we actually apply the rounding, I do want to select only the var1 pred. So I want to leave var1 var behind, and also while selecting, I want to rename var1 pred on the same function. So let's call the dplyr : select. I do want to select that var1 pred. So I want to type it out, var1.pred, but I also want to rename it on the same function. So we just come before it. I want to rename it to cluster_f to mean that it was that it has already been the focal filter has already been applied. And then once we do that, I want to give another pipe and then do the actual rounding. So to round it, we're going to use the function mutate. I want to overwrite the same column name. So we use cluster_f as well, which is the same name that we just gave it on that select. Say equals, and then we're going to say use the function round, which is also rounding that cluster_f, right? It's still rounding that. and then comma, and here is where we say how many decimal points we want. I want 0. Okay, so if we go ahead and run this and print it, now we have that back to being either 1s or 2s. If I do a summary, even though the summary does give us like a mean here, but this is just calculating the mean. It's not actually that, this is not the actual mean of the data. And the reason why it's still giving us like a statistical summary when we print the summary for that column is because it is numerical, right? R is interpreting it as numerical, which I do not want to. I want R to interpret that as a categorical variable. So let me ask someone here in Athens, how do we make R interpret this cluster F as a factor or categorical instead of numerical? Any thoughts? Yes, Bo.
Can you use the mutate?
Yes.
I
So,
think this project,
just give me a sec, online, just, so Bo here was saying using a mutate, that's right?
Cluster that.
Yes, that's exactly it. Thanks, Bo. Sorry, someone online said something?
Yes, sir. I'm getting an error saying that cluster F is not found. Could you scroll back up? I'm not sure why I'm getting that error.
So cluster F, so here's where we created basically cluster F when we renamed var1 pred to cluster F. That happened at this stage
Right.
here. And then make sure you have a pipe connecting after that. And also before it.
Yeah, I have both of those. And it's var1 period pred, right?
var1 dot pred, yep.
Okay. Huh.
Make sure.
Let me-
So I don't know if you all noticed this, but whenever you have either an object or a column that's named the same, if you select one instance of it and you have like neighboring within your view, if you have more columns named the same, they kind of get highlighted as well. So you can see here that when I highlight cluster F the first time that we typed it, I can also see the same downward, like wherever we type afterwards as well. You know, if for some reason you have a typo on the first time or maybe the second time, when you do highlight it, it would not appear, right? So let's say if I had cluster with a capital C the first time, it doesn't highlight the other ones. So that maybe is a good way of finding flow. Let me know if you're able to troubleshoot it.
Yep, I was able to get it. I'm sorry. I didn't run the chunk with that var1 pred up above, so it didn't know where to pull from. Sorry.
No worries. All right, so Bo said here that we need a mutate. So again, what we're trying to do as the last step here is just to go from numerical to categorical. So Bo was saying that we can use cluster F equals factor cluster F, and that's exactly right. I also just want to, so we've been using factor. There is a function that would be called as.factor, which it's the same. It has the same effect, but if you do come across that, I just wanted you to be aware of it. But I use factor maybe because it's a little bit shorter, but I just wanted to point that out. Okay, so if you follow through till here, and then we just get a summary now of zone S. Now we see that we do not, when we do the summary of that object, cluster F does not return a statistical summary anymore because now it's been interpreted as a categorical or factor variable rather than numerical, right? That was my goal at least. All right, so we did a lot of stuff in this chunk here, and we have not printed yet. And I guess if you were doing something like this on your side, as when I was doing this the first time, I played around a lot. I Googled a lot to find what functions I needed. I'm giving you that sequence. And of course, every time we do something like anything that we do in code, it's always useful to plot the results to make sure we're getting what we are expecting that we're doing. So let's just come to the next chunk here. I think I left you all the code there. If you just run it, yeah. So you can just go ahead and run that code. I left you already the entire code. I do want to walk you through a few things here. So zone S, I'm just going to print zone S. It has that column called cluster F, which is the column that we have applied the focal filter, interpolated to the field boundary. And at that point, it was all numerical and then finally transformed that to categorical, right? So that's what cluster F is. I am giving the fill according to that column, right? So the color is changing depending if it's a 1 or a 2. I am bringing in the boundary, changing the scale color. I am changing the title here. So I do want you to make sure you understand this, because you will be asked to do this in your assignments, and I will be picky. This, I do ask you to change your title as you're developing different plots. This is where you would do that for the assignment. Yeah, I guess that's pretty much the only detail I had it. So let's just go ahead and print it again. So this is what our map looks like. And again, it is quite possible that on your side, the cluster on the left is orange and on the right is black, and your numbers here of 1 and 2 are flipped. That is completely possible because K-means has that random first step, and because of that random component of it, it may flip your assignment of clusters. That's completely fine. It is expected. We just have to be aware of that, especially when we get to the end of this exercise. However, this is what we look like. This is what it looks like, right? So I just want to pop out this window here of the unsmooth zones. And I want to come down to the 5x5 mean window and the result of that. So as you can see, that window size and using the mean function, kind of interesting that I'm just noticing that for mine was flipped that way as well. I guess it doesn't really matter like where the colors are, as long as you know the shape's still there. So maybe on your side you're still seeing the same colors, at least on your screen, on both sides. On mine they flipped. But we see now that when we use a 5x5 smoothing function with a mean operation, it pretty much removed all of those intrusions of one into the other, right? Which is what we wanted to do. So at this point, I would say, okay, we developed 2 zones. They are compact, cohesive zones. The implement that this farmer is using is not going to be changing rates for a very small area like it would have been before. So this is, I'm happy with this as is. I do want to ask you to export or to save your plot. I left you already the path, the name. Notice how the name has the window size 5x5 and also the function we use, which was the mean function. You will be required to change this on the assignment. So just pointing that out. Make sure you do print this one so you can just reuse that for the assignment. Okay, so the next thing I want to do here is it should actually be pretty straightforward. Is just to, if you think of it, on the previous exercise, we have validated our cluster, not our clusters. We have validated the yield spatial temporal stability clusters, which I guess I'm using the word cluster, but we didn't really cluster them using any statistical algorithm. They were just the result of the yield data across 3 years. So now I want to bring back the terrain and EC data so we can validate these clusters that were actually using those field EC and terrain data to create the zones. So for that, come to the next chunk here. So my goal is basically to join the Zone S data, which right now has 4,032 rows, and it only has a column that is telling us what's the cluster ID. I want to join that with the object, the all-v object that has all the terrain data that we use to create the clusters. So to do that, come to the next chunk. We're gonna start by calling the zone underscore S. Gonna give it a pipe. And to do a join, remember zone S, and we're joining with the object LV. They're both SF objects. Because of that, we're gonna use ST underscore join to do this join. Every time we're doing spatial joins, the first thing is the data that we want to join to. So that's called all underscore V. It was one of the data sets that we brought in the beginning. And I just printed that below here so you see what it has. So it has the standardized yield for each one of the individual years. It has the mean standardized yield across the 3 years, the standard deviation, coefficient of variation, the ST class, and then all the field data as well. When we're doing this, the ST join, we do want to change a few arguments. So one of them is the join. So we want to change the join argument to be ST underscore equals. The default is another one, I think is ST intersection. That's why we're changing it. And we also want to say left equals true. So it does a left join. So if I run up until this point and I printed, the resulting object has that cluster ID that has been already smoothed and interpolated, and then all the other field data as well. I do want to select out a couple of variables here just to keep consistency. So add a pipe, let's use dplyr : select. I want to select out full direction and aspect because those were the two that we did not include in the management zone creation. So to select out, we use the minus symbol and then the variable name. The variable name is flow_dir. So I say minus flow_dir, comma, minus aspect to select out those two variables. And that's pretty much what we had to do up until this point in this chunk. Okay, so my goal next, and I left you, I believe, most of the code for what we're doing because we have already gone through the explanation of that code on the previous project, is to create box plots. So before we created box plots where our X variable was the ST class and our Y variable were the values of the different terrain and EC variables. Now we're going to do a similar thing. The difference is that I want to create plots, box plots, where the X variable is actually going to be the cluster. So it's going to be either 1 or 2. So if you come to the next chunk here, I already left you most of that code. There will be some things that you need to change, but I just want to walk you through. So this code, very similar to this, we have already done on the previous exercise, but I still want to walk you through a little bit. So I'm selecting out ST class out of here because we really don't care about ST class, at least not for this coming plot. And then I'm doing a pivot longer, right? So I just want to show you before the pivot longer, we have 4,032 rows. And then I'm saying to pivot longer the columns between elevation and ECA 90. So we would be pivoting longer only elevation, slope, ECA 30, and ECA 90. Those are the columns that will be pivoting longer. So if I run until here, we basically 4 columns, so we should have 4 times as many rows as before we pivoted longer, because now, I mean, you know what pivot longer is doing is basically taking those columns that were side by side and putting them below each other and creating a new column that is called name and a new column that's called value, right? So we've seen this before, this is not new. I do want to change a few things here though. So if you come online, at least for me, it's 353. On the X, I want to have the cluster ID, right? So in that, on this data set is called cluster underscore F. So change that. So we have cluster either 1 or 2 on the X-axis. We have value. So the value being the value from one of the variables, that elevation, slope, ECA 30 and ECA 90. And then I'm coloring by cluster as well. I'm adding a geom box plot. I'm changing the scale color to be colorblind. And then I'm using the facet wrap to facet. I guess I can just comment off this plus here and run so we can see what's going on. This is what's going on. So again, to do this very quickly, the two magic functions that help us to do this is one pivot longer and the other one is faster wrap. Pivot longer acting on the data level, faster wrap acting on the plot level. So I want to show you here. So we talked about this before where we do have the box plots, but how do I know if they're statistically different or not? So before we had a whole chunk where we ran ANOVAs, extracted means, did pairwise comparisons. We could do that here as well. However, there's an easier way of doing that because we only have two groups. Since we only have two groups, I just need to know if one mean is different than the other. There is an easy way to do that, like on the go, that we don't on the fly, that we don't really have to code a lot, which I want you to come on this line here that I have commented off 3 dots, delete those 3 dots and the hashtag as well. And I want you to include here the function called stat_compare_means. This function is coming from the, let's see which package. Here. From the ggpubr package, which I think was one of the ones we installed in the beginning of this exercise. So it has, let's see, if I just run it into here, what does that do? Okay, so it adds some text and some stuff on top. I just want to change the default behavior of that. So if you come back to stat compare means, I want to say label equals open and close quotation marks. I want to use the label format called p.format. So it just changes the way it looks like. And then I just want to change where that label was placed so we can better see it. So inside stat compare means, add a comma. We're going to use an argument called ageJust. That's to change the horizontal justification of that label. I want to say equals -0.1. And then I want to add a comma, and I also want to change the vertical justification using the vjust argument to be equals to 1. And then after that, just make sure you add a plus on that closing parenthesis so it connects with the last function, the theme function. Okay, so if we run this, this is what we get. So this, if we had done an ANOVA and we had extracted the p-value of that ANOVA, that's what this p-value here would be. So if you...
Can you scroll it when you get a second? I didn't get all that.
Yeah.
Thank you so kindly.
Yeah. So here is basically given as a p-value, and if you're not familiar with it, is basically a value that if the convention at least is that if it is below 0.05, then those means are significantly different. So you can see that p-values here are all well below 0.05. It's using like an exponent notation here, where it's just saying that all p-values here are less than 2 to the exponent of or to the power of -16. So that's a very, very small number, meaning that all these box plots here are different between themselves. So if we just stop for a moment here and think about it. So we're having, so ECA 30 is higher. So shallow ECA is higher for cluster 1. Deep ECA is also higher for cluster 1. Elevation is higher for cluster 1. And slope is also higher for cluster 1. So basically cluster 1 has everything higher in this case. And of course, even though if we just look at the map that we created here, these zones are not the same as the yield zones that we created before, right? Remember that these zones that we just smoothed out did not take into account yield data. It was just terrain and EC data, right? So we're basically creating, almost like creating 2 different zones, one using only yield data and one using everything except yield data, and kind of comparing them side by side. We see that they do have, some commonalities perhaps, but they're not matching completely, which you wouldn't expect because yield data was not seen by the k-means algorithm. But I guess, if we just think about it, based on what we learned of the terrain and EC variables on the previous exercise and how we classified or not classify, but how we use them to explain the high stable and low stable. Let's think about those. So if I had to summarize cluster 1 and 2 as being high or low yielding, I know like I'm not giving you all the data you needed to make this interpretation because we're not looking at that at the box plots that we created before. But if we were to connect these box plots of the effect of VCA, shallow, deep, elevation, and slope on the clusters, and then connect that with yield, that we saw the relationship of yield variables with these same terrain variables. Can anyone have a guess if you think that, in my case here, cluster 1 has everything higher, maybe on your side, cluster 2 has everything higher, which again is because of k-means random first step. But regardless, in my case, if we think in what we're seeing on my screen, which one of these clusters, 1 or 2, would you expect to have higher yield? If you can mentally make that connection between these variables and what we did in the previous exercise with yield. 1, right? That's a good point, but we're not addressing that right now, right? So some people here in Athens said number 1 would be higher yield. I agree. And then Amrinder made a comment, it depends on weather. I also agree. However, something interesting is that we did not use weather variables. We did not use yield variables for creating these zones. So the only thing that the k-means saw was these 4 variables here, and they have no relationship with weather in themselves, right? So the algorithm has no way to know that some areas are unstable because of weather, as is, right? But that's a good point. Okay. So let's come here to the next chunks. I basically now, so we saw how these variables, the terrain and EC variables affected cluster. Now I want to see how other variables affect clusters. So the next variables I want to see how they affect clusters is this. So let me just print zone SDF. I want to see how SY 17, 19, and 20, which again were the standardized yield for each one of those years, and this is a percentage, right? How they are affecting clusters now. The only thing that we have to change in the code, I basically just copied and pasted the code from above. The only thing we have to change is which columns we're pivoting. So if you do come to the next chunk here, we're gonna basically be pivoting SY 17, 19, and 20. So I can just write here on these 3 dots, if you want to go there and delete the 3 dots, I can just type SY 17 and then colon SY 20. Yeah. So that basically selects the 3 columns that is starting as SY 17 and then SY 20. If you just run that, it should work fine on your side. So now we see again, the p-values are all less than 0.05, meaning that the box plots are significantly different. And as you know, some people here guessed, and maybe you all guessed on your heads as well, cluster 1 has the higher yield in all 3 years, at least on my side, cluster 1. Remember, it may be different on your side because of k-means. But so cluster 1 had higher standardized yield in all 3 years in my screen. Even though, especially like in SY 20, you had a lot of variability, right? And again, because the way that we train k-means here did not take into account weather, did not take into account yield, all of those unstable areas, and even some of the different areas that we had before are kind of mixed within both clusters, really. Okay, so the next box plots I want to create is basically the variables I want to have on the y-axis are the mean yield and the CV yield. I just want to print zone SDF here again. Now I want to have the mean pixel and CV. Excuse me. I want to have the mean pixel and CV pixel as the y variables. And again, the only difference in the code is just which variables we change on pivot longer. So now, because we're given two columns that are not consecutive, so there's a nasty pixel in between them, we have to give them, like, spell out their full names. And because we're given two columns, we need to use the C function to concatenate them. So we come here and we just say, within the C function, we say mean underscore pixel. We give it a comma, and then we give a C underscore or CV underscore. So mean underscore pixel and CV underscore pixel are what we need here. And then we can just run them. Let me show the code still. Let me see if we can do this so we can see both code. Yeah, that's not gonna work. So let's just take a look at the plots first and then we'll see. So on the CV side, even though both of them have lots of outliers, but so they're both CV and mean pixel are also less than 0.05, so significantly different. We see the CV on the cluster 2 is higher, right, than on cluster 1. And then mean pixel, so this would be the mean standardized yield on cluster 1 was higher across those 3 years compared to cluster 2. So we're seeing here that cluster 1 has higher yield in all of the 3 years. It has a higher yield on the average of the 3 years, and it has lower coefficient of variation across those 3 years when compared to cluster 2. Okay, so I just want to write down here on my side, and I want to invite you to write down on your side as well, because on your side it may be different. So you do have to think about this yourself.
So,
Mhm.
your CV on this that's higher CV on this second one, on the right.
So this variable that we're looking at on the first panel is CV, right? It's CV by itself. So the CV across 3 years was higher for cluster 2, right? Like, and I'm saying higher based on the median, so on the center point of that box plot. And then on the mean pixel here, even though this also has a CV on this distribution, but that's not what I was referring to. I was just referring that mean pixel across 3 years was higher for cluster 1. Oh, wait, class today ends at 10, right? And I had in my head that it was 10:10. So I'm sorry, everyone. Yeah, I guess we can stop here. We can finish this next class and I'll give you an assignment next class then. Yeah, we can wrap up. If you have any questions, I'll be here for a few more minutes. And sorry, I thought we ended at 10:10 today. Sorry for keeping you longer.
Did you scroll back up? I didn't get that last part, Dr. Bastos.
Yeah.
Yep, thank you.
All right, yeah, sorry for keeping you a little bit longer, and I'll see you Wednesday.
Their attendance on GitHub.
Yes, thanks. Yeah, let me take attendance as well. Thanks, Trip. All right, I just submitted the GitHub issue. If you are still watching, claim your attendance. I guess if you're watching on YouTube later and you were in class, but you had to leave before, feel free to claim your attendance as well.